right, so I think it's really important that we stop for a minute and say, what is science? That's one of the big things I want you to get out of this class, a clear understanding of what science is, how science works. We're learning astronomy as a case study, an example of what science is. So, what is science? What makes some things be science and other things not be science? What defines science? Well, first of all, I'll say science is a social movement. A social movement. It's something done by groups of people. Individual people alone, well, you got to talk to other people. Yeah, that's an essential part of what science is. So it's done by groups of people working together, collaborating, arguing, disagreeing, trying to disapprove each other's ideas. Science is a social movement. It's groups of people working together on the largest possible scale, many different people all going their different directions, but they're kind of agreed to some ground rules. These ground rules laid by the ancient Greeks, this idea that we're going to try to understand the world around us in terms of rational, logical principles and ideas. What we're going to do is we're going to try to figure out the rules of the universe, how things work. We're going to do that through observation and through testing our ideas and all this. And so oftentimes these are taught as what we call the scientific method. The scientific study the scientific method in grade school and all these sorts of things. So what are the? And I think there's a great deal of truth to this. I want to go through this idea of the scientific method and then talk about how does this really apply to real science as it is actually practiced in reality today. So first of all, in the scientific method, what do we got to do? We got to, first of all, we have to have observation of the natural world. Every science has people, has scientists out there observing the world, whether it's in the laboratory, out of the laboratory, wherever you are. Observing, making very careful, detailed observations of it. So observe the natural world carefully, in detail, and what could be more detailed than specific numbers? So measuring specific numbers. Measuring specific numbers. Measuring specific numbers. That's absolutely vital here. I don't just observe this star is hot. I observe its exact precise temperature. Observing the natural world is an essential part of the scientific process. Okay, what do? We make our observation. Well, that's not enough. We observe and look for patterns. We find interesting patterns in our observations of the natural world. And then we try to understand these. So we propose hypotheses. We propose ideas in order to explain why these patterns. So we look for patterns. We propose hypotheses to explain these patterns, ideas for why it is. Okay, why is it that this group of stars are all kind of reddish, whereas stars over here aren't? Well, okay, so my hypothesis is, well, this is all a group of old stars, and then so they've turned red over time, and then we can go about the details of this and testing this out and trying to figure out the specifics of that. That's an essential idea behind this. So we're going to propose a hypothesis in order to explain that. And then we test our hypotheses. We test our hypotheses any way we can. If we can do it experimentally, great. If we can do a controlled experiment in the laboratory, that's a wonderful, fantastic thing to do. A little bit hard to do in a lot of astronomy. It's like, okay, take one rotating supermassive black hole, add 2 giant planets, and well, okay, that's kind of tough to do. So what do? Okay, so we test this through more observations. We test our hypothesis. How do you test a hypothesis? You use your hypothesis in order to make specific predictions, and then you see if they're right. Okay, if this is right, then if you observe these stars, you'll find that the chemical composition of these stars varies by blah, 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 and then we do the details of all that sort of thing. So that's how we put things to the test. In the laboratory, if we can. If we can't do it in the laboratory, then by making specific predictions, which can be tested. Okay, let's do that a little more. And so we have observe We look for patterns. We propose hypotheses to explain these, and then we test these hypotheses by making predictions, and we verify them. Or we deny them. I mean, maybe they're not right. And so we figure out one way or another whether they're right or not. If the predictions are wrong, the hypothesis is wrong. It goes out the window and we try to propose another one. If, on the other hand, we have a hypothesis which stands up over a long period of time, making lots of predictions, figuring lots of things out, well, then when it really works over a broad area, then we can call it a theory. And so we might get to that. So here's kind of the classic scientific method is maybe taught in middle schools throughout the country. Is this right? Is this truly how science works? Well, I wouldn't say it's true in terms of a step 1, step 2, step 3 part of the process. It's not like, okay, today I'm a scientist. Today I'm on step 1, I'm going to observe. Tomorrow I will find the pattern. Step 3, I'll propose a hypothesis the day after that. No, forget about it. These are things which must be happening for the activities of a group of people to keep together be called a science. That's a key idea here. It's not like, there are scientists who totally specialize in all their whole careers. They're just coming up with hypotheses. They're doing theoretical work. Others specialize in observations. They do observations. That's what they do. Others do experimental work. You know, we specialize a ton in the sciences. So this is all going on. However, in order for a group of people, the activities of a group of many dozens, hundreds, thousands, hundreds of thousands of people all around the world, in order for this group as a whole to be, say, okay, together, this is a scientific community. These people are doing science. In order for that to be true, then you must have people who are observing and people who are proposing hypotheses and people who are testing these things. And so I would say the scientific method is true if you apply it on a global scale. There are plenty of scientists who never, get to every single step in the scientific process, and certainly not done in a linear fashion. You don't do step 1, step 2, step 3, step 4. Constantly, all the time, you have different people observing and testing and proposing hypotheses, denying them, and by testing and observing these things, well, you're making more observations, so this is a little bit of a cycle. You're testing this through more observation, so these two steps in a way are really the same thing. There's the general observations to test hypotheses, and well, these are all interconnected. And so you constantly got these things going together in a cycle. And so this is one of these are kind of the essential ideas, the essential steps of the scientific process. And of course, I gotta mention the importance of math in all of this. That science requires us. Okay, so again, got to talk about math. Math is huge. Math is especially in astronomy and the physical sciences. Astronomy, physics, these sorts of things. Chemistry, shoot, even biology these days includes a ton of math. And so mathematics is a necessary and essential part of the scientific process. So when we say observe, what we mean is we measure specific numbers. Specific numbers. When I propose a hypothesis, that's not just some idea, some set of words, to do that. Usually, a hypothesis in astronomy, I'm talking about a set of equations. Hypothesis, or a grown-up hypothesis that's really worked a ton all over the place. Well, that becomes a theory. Theory. This is a mathematical thing. These are equations. Or other mathematical structures. And from these, what do? I can then predict specific, precise numbers. And if this theory is right, I can go out and measure this star. And well, because this star has a mass of 2 times the mass of the sun, its surface temperature should be exactly this. And its total luminosity, the total energy it's putting out should be exactly this. And then I go out and measure those things. And if I have a theory which can predict those specific numbers before I measure them, and it's right, then that's taken seriously. That's the real evidence behind this. So I'm observing specific numbers. My hypotheses are equations, systems of equations, other mathematical structures. And then the testing of a theory, the testing of a hypothesis means take the theories predicted purely from equations, and these numbers predicted from equations, measure them in reality, and compare them to each other. And if the hypothesis predicts numbers that are the same as the ones we observe, then we take it seriously, and then we test it some more. And if it works all over the place, then we call it a theory. And a theory is therefore a set of equations that allow us to predict a wide variety of phenomena. Predicts a lot of specific numbers I can go out and verify. When I talk about like the Big Bang Theory, the Big Bang Theory isn't just some idea. You've heard it summarized in the newspaper or on television or something like that. The Big Bang Theory isn't just some words. It's a set of equations that make specific predictions about how our universe began and how it works and how all these things go. So this testing sort of thing means comparing numbers. Comparing numbers. You compare the numbers that come out of your theoretical equations, and you compare the numbers that I observe with my telescope and my light meter, and if the numbers match, then that's considered strong evidence. And that's why we use so much math in the sciences, because math is about details. What could be more specific and precise than a specific number? And so if we can get the numbers to work, then we say, hey, my theory, my hypothesis just may have something to it. And that's my quick summary of the scientific process, what it is that makes science work, and how it's become such a fantastically successful social movement, how it's become such a fantastically successful enterprise, is because all sciences have these ideas, these steps, these processes going on, being done by different people. Wonderful.